Hello, welcome to the overview presentation of Structures Office 1.0. 1.0 addresses the construction of arbitrary compact cross-sections. It does geometric, elastic, and plastic section properties. It does restrained and unrestrained bending analysis. And it does plastic analysis, which is calculating the rupture moment on a cross-section. And last but not least, it's fully programmable so that it can be integrated in Excel or MATLAB or any COM-compatible language like Active Perl, Active Python. So let's begin by creating a cross-section. So this is the user interface of version 1.0. It's going to change over time. There'll be new functions added with each new release. Let's just quickly run through what the user interface is. Over here is your style button for changing the style of the interface. Here's your file operations, the new open save as, and then exporting section properties as XML or the shapes as a polygon. And here's your recent documents. Here's your quick access toolbar. It's set up for the new open save and then full view, rubber zoom, redo, and undo. You can control what's in the quick access toolbar by clicking on this button. It will give you a list of groupings of functions which correspond to these tabs here. Any function that you see here, you can simply run down, find it, and click Add to add it to the toolbar. This area is called the ribbon. It's got 3 tabs, which is groupings of functions. Each tab is further broken down into panels. In this case, it's Edit, View, Shapes, Point Operations, Transformations, and Boolean Ops. The Edit panel has the undo, redo, delete, and change the sign. The viewing operations are full rubber zoom, showing units, showing the IDs of objects, controlling whether the grid is in front or behind, changing the background color. Here is the shapes that you can use. There's the basic primitives of rectangles, trapezoids, annulus, general polygon, and then higher level function shapes like T's and L's and Z's, and there's formed versions and extruded versions. The point operations is to analyze the section to see distance between points, getting angles of 2 points or 3 points, adding new points to help in the construction. And then there's the translate and rotate mirror, and then the union is a Boolean operation to combine shapes, eliminate overlaps. Here is the tree, the section tree. We'll talk about that in a minute. So let's get started. And let's start out with adding some subsections here. I will call this the upper chord. And let's add a lower chord. And then let's set this current to the upper chord, and let's add a T. And let's make that and 135. I'm just hitting tab to move between the input cells. Anything goes here. And let's just click apply and see what we got. Okay, so let's say we want this section to be oriented so that this top of this web is horizontal. And you see that these points correspond to these points on the section. If you have any doubt, you can always go up here, click this, and say show position points. So I want to set the origin to 7 and the direction to go to 6 across the top. I want it to be horizontal, and I want to keep the origin point at the origin. So I click apply. Okay, so now I have my cross section, and let's say I want to mirror it. So let's pick that object I want to mirror and click mirror vertically. I want to mirror about this point up here. If I click this point, the coordinates will go in there. Click OK. Okay. And let's add a bulb. Let's add, okay, first off, let's get the distance between these 2 points. You see it's 0.4, and all the outputs are shown up here. So let's say I want to add a disk. I want to locate it, so I'm going to click on the X or Y. I want to position here. I want to get the radius, and I can click these 2 points to get the distance between that. And then I can click Add, and now I have a bulb shape on that flange, and we can turn on the union. Now if you go over here, and you see that the union eliminated that overlap of the disk on that web, and we see that this upper chord consists of a T and a disk, and then they've been unioned together. So now let's go back up to, let's go create the lower chord. Now all my inputs are going to be to the lower chord, and let's say I want to add a L, and we'll make that. Let's click apply. Okay, now we have an L. Now let's set the view back up to the, right, let's make the root the current section, and we see both sections. Okay, now let's position this web on this, right at the top of this flange here on this web. So I'm going to create a point on this section, and I'm going to say point at distance, and I want to go up 3.5. So that's going to, the vector is defined by the first point to the second point. So it's going to be 3.5 inches up from here, and that's my point. And now let's position this flange over here, so I can click this point, and then I say, I right click and I say move object's vertex to match vertex, because whatever point is associated with that shape is what's going to move. So I'm going to move that over there, and let's click full view, and now I want to let's find out what this angle is. So it's 315 degrees. I'm going to want to rotate this thing 45 degrees clockwise direction. So that's a negative angle. So let's click, I want to click this section and rotate selected, and let's pick this point, and I see that those coordinates went up here, and let's say minus 45, and click OK. And let's go back and get our full view. So there's our basic shape construction. Okay, now let's move into the analysis of this section. One of the first things you'll have to do is create a new database, material database, and I will just stick it, we can just put it up here on OneDrive. And I already got one. I'll just say I'm going to overwrite it. And okay, so now you can show the path to what the current database you are using. You can see the materials, and it just, the default database just creates an aluminum and a steel. Well, if you wanted to see what that definition was, here's all the specifics on this material, and we'll go into this in more detail when we get to the plastic analysis. So let's apply some materials to this. I'll just set it to aluminum. And now I'm going to mesh it, because some of the section properties calculations require a mesh. Mesh selected, and let's say I want to put 500 elements in each one of those objects. And you'll notice here the chord height tolerance for these curves. This defines how tightly that mesh will match these curved objects. And we're doing a 3-point triangle. Click OK, and there's the mesh. If you go over here, you'll see underneath the root we have a mesh, and that the materials were defined on this upper chord object and in the lower chord object. Okay, now let's just go. So I thought it might be a good idea to just quickly walk through what the definition is of some of the section properties being produced by Structures Office. The elastic section modulus is it's the second moment of inertia divided by the distance from the centroid to the extreme fiber relative to the centroidal and principal axes. And it's used to compute the yield moment. So it's simply the elastic section modulus times the yield stress to get the yield moment. For the plastic neutral axis, we're looking for the location where the forces above and below, where we're assuming that we're going to a fully plastic state where it's simplified as simply a rectangular area above and below that's fully yielded. So the plastic section modulus is the sum of the areas of the cross section on each side of the plastic neutral axis, and they may not have to be equal, multiplied by the distance from the local centroids of the two areas to the plastic neutral axis. So it's simply the area in compression times the distance from the centroid of this area to the plastic neutral axis, plus the area in tension times that distance to the centroid, the tensile area. And it's used to compute the moment capacity, which is similar to the elastic section modulus, where it's multiplied by the yield stress to get the moment capacity. And the K factor is the ratio of the plastic section modulus to the elastic section modulus. Go over to the computation interface and click section properties. Okay, here's your geometric section properties. There's the area, center, gravity, principal angles, moments of inertia relative to the centroid, moments of inertia relative to the axis system, radius of gyration, principal moments of inertia, and the elastic section modulus. These are the elastic properties because we use the same material on both portions. There's no difference between the geometric and the elastic. And then there's the plastic section. Now for the plastic section properties, as I just went through, this is a location of the principal neutral axis relative to the centroidal axis system. Here's the plastic neutral axis relative to the principal, the plastic modulus for the centroidal axis system, and for the plastic, and the K factors, and then the moment capacities for the centroidal and principal axes. The elastic and plastic bending is a little too much to cover in this short introductory video. So see the training section of the website at www.structuresoffice.com/training. Well, thanks for listening. I hope you enjoy the program, and please send us your comments, particularly anything that you're looking for that's not in the program in 1.0. Thank you very much.